I've been focusing on understanding the standard model and wanted to figure out how gauge interactions work and just trying to see if they would lead to quantum gravity. So let's start with the basic one, which is just going to be a regular old U1. This is for electromagnetism. It's like a 1 by 1. It's just essentially all the ways that you can um, form the number 1 using e to the I theta. So the magnitude of this really is going to be equal to 1. Okay, so this is just a one generator, one-dimensional thing. So you can imagine it kind of like this. You would have like a length L here. This is like a radius, I guess. Radius. And the idea is here you're at 1, here you're at I, here you're at 1, -1, and here at -I. And the way you can do that is just by changing e to the I theta, is change the angle here, and you can go around the circle. But of course, it's just a one-dimensional circle. So, it seems like you might have 2 dimensions here, but really it's just one L. And so that's why we have this one complex plane. There are infinite angles here. But okay, so that kind of gives us the idea of the U1 group and how we can sort of spin around in different ways. You could take any number and just spin it around. It's like a scalar. Okay. And over here, we have a 2 by 2. So this is the weak. So now we're getting to the SU2, which is the Pauli matrices. Some 2 by 2 matrices, as you can see. They're just 1s or negative i's or negative 1s. It's nothing too complicated. I mean, all we're really doing is we're taking this little loop that we had here, and we're making 3 of them. So this makes kind of a 3D volume here. Of course, it's more of a 3D complex volume. So the only real part of it is actually this little plane right here. You can see we're going 1, 1, -1, -1 corresponds to like a cosine of 0, sine here of power 2, have the cosine here of pi, and then sine over here, 3 power 2. This gives us the real part. And the imaginary stuff is all just kind of on the sides over here, but at this point we start to see this little arrow popping out here. Let's sort of discuss what that means. If we go back to this U1 and we look at our length of time here, and we can clearly see uh, how we have the 1L on this side, we have a 0 right here in the middle, we have the -1L over here, and if you have the energy levels, so E1, this is E1 right here, E2, and then E3, you can see how at every energy level you're hitting points along the I or the negative I, depending on whether you're, so you get this sort of you basically get this sort of a spherical version of what we did here with the rotation, but it's more of the probability wave function here. And you can see this is just a circle, just kind of outlined like that. So you're hitting the -1s, the i's, the negative i's, as you're sort of making this temporal moment. Now, oh sorry, the length here, energy, the energy wave function essentially for the length of L. And what we did here to get a temporal moment is we had to sum up all the different possible L's. So we go all the lengths of L's from 1 to infinity, and as you can see, kind of have to split this apart depending on what we have, evens or odds, whatever, that's just different stuff, don't worry too much about that. The idea is we now take the energy, well, if we sum up from 1 to infinity, what we get is a zeta function, because we're getting L to the 1/2 right here. So we have a zeta function starting at a half. And if we want to add the time component, then we have to consider the energy levels, because that adds the time component here. So we can start to analyze this stuff over time. So we get a temporal moment as the energy starts to move over time. And this obviously corresponds to the Riemann zeta axis here, where we have those imaginary zeros popping out, which is interesting. We haven't figured out exactly how it's going to fit into everything, but it's okay, we'll get there later. For now, let's just realize that we have a temporal moment, sort of an arrow that's popping out that way and it's pointing one direction. It gives us a nice little situation over here, because if we're looking at um, this SU2 here, you see that the area points this way. So this gives us one direction here, uh, at least in terms of the time, I'm sorry, the real. And of course you could pop up on this side or on the bottom side. It's like this, so this is kind of determining your spin direction, or your ups or down. And that's the point of the SU2, is to flip you up or down. So kind of tells you whether you're on this side, that side, or which have you. Okay. And that's interesting. So obviously there's infinite possibilities here. There's like basically just a probability and of where we're going to find the position. But as we go into SU3, we have the 3 by 3. So this is the strong force. This governs the colors. So you can see we kind of have colors forming. Where would they form? I was thinking, well, we're getting 3 areas here. And we have the ups and downs for the colors as well. There's like anti-up and the green anti, whatever. So there's basically the anti-color and the color. So that's why we have the ups and downs for that. And you can see how there's 3 areas forming. There's basically, in order to get this, we realized we had to take this and make a little triplet here. But if we take this and we split it apart and we sort of connect it like this, what we get is our 8 generators, because this sort of has to do with how many loops we put together. 3 loops gives you this thing, which gives you the 3 generators. 8 loops, this isn't really quite 8, this is 7, but essentially there's one more somewhere over here. These essentially give you the 8 ones to get. 1, 2, 3 for this guy, 1, 2, 3 for this guy, and one extra one here, and then there should be an extra one somewhere else that sort of connects them a little bit more. And this is it's just really freaking hard to draw that. But yeah, this is the SU3 groups, and you can see how we have, this is again just the SU2 group repeated, but in a sort of a higher level space. And then this is sort of the inverse of that, as you can see here. Unfortunately, this one had to be a little bit twisted in order to actually get all the calculations correct. But this is supposedly the inverse of that. And then the these guys on the edges, notice how they are able to mix these guys together. That's why we have this larger circle here and then these smaller ones over here. So we're kind of getting these different ways of forming these areas, real areas. And these real areas form essentially the symmetries of the SU3 group. Now that we head into the 4th level, this is where we have to deal with the gravity situation. We have the sort of 3D space forming in a 1D time. And that is how we sort of symbolize this -1 here. Represents that it sort of is different from, you could sort of think of this as a subspace here, and then this is like just time over here. Okay, so it makes a lot more sense when you think of it that way. So what we had to do is we had to stack these tesseract spheres, the tesseract spheres, which is just a double Riemann sphere. The Riemann sphere is essentially a sphere that has real and imaginary components. So we're just stacking them up. This is essentially a double or a triple one, kind of, however you want to think of it. And this one's when you get to the quadruple of it. As you can see, 1, 2, 3, 4. Now here's where the negative I of this one is, negative I of that one, negative and positive I of that one, positive I. So this one has a negative I and a negative I, and then there's a positive I and a positive I. They all meet together in the center here. They form this quadruplet, and it equals 1. So it's only a positive, just a regular old real volume here. So what we have is essentially, notice this is 1 is the negative 1, because what we would have is, maybe a 1 times a negative 1. Right, and then over here we have just a 1 times a 1. Here we have a negative 1 times a negative 1. Here we have 1 times negative 1. So we just have a real volume forming inside of this quadruple Riemann sphere. And this is why we have real volume. Okay, there's literally a 3D volume of space here forming. Whereas over here was more like areas. And here it was like different faces of the area. But here it's actually like this is a solid volume. And every little tiny spot in here, it looks like a web, but it's actually a solid here. That all of this can be represented by some x, y, or z coordinate. That's all you need to represent this. That's really all you need. You don't need any of the eyes, because the eyes, uh, there's already a component that represents that component. So like you can follow the eye line, down. Let's say you followed it down to this. Because you're here now, or anywhere in here, you can use the other real components from the other three spheres to form that vector. You don't need this eye over here. So you can essentially translate anything you want from I into real just by using this sphere here. And this is essentially the spin network. And of course, if you just recall that each one of these little um, areas, or each one of these little L's that we have, these loops, they have a little temporal moment. This is where I'm getting a little bit stuck on, is how we're going to align the temporal moments with, say, for example, the gravitational field or something, so we can develop this quantum gravity model a little further. But let's just realize that now we have indeed seen how we can build a 3D volume, and at any one of these points, we can oscillate between the real and imaginary component. And if we do that, we're going to get the Schrodinger equation, right? Because we have the d psi over imaginary time over here, do all this stuff, and then you can get the see if I can remember the Schrodinger equation. Maybe there's an I over here. There might be an H bar. Uh, you know, and then over here you have the Hamiltonian uh, of the sign. So I can't remember. There's an H bar here. I think there is. Oh, maybe it's just a regular old H. But this is essentially what the Schrodinger equation is trying to tell us. It's trying to tell us that we have a quadruple Riemann sphere where uh, we have the three real components are sort of coming together and making this XYZ volume. And as you can see, all we need is negative ones and ones and ones to form all of the generators. Because the eyes they're there, but we don't need them. We can reference them if we want to figure out quantum mechanics of what's happening at every point. Every point in time, you can take the derivative, the partial derivative of that wave function, and see what the energy is doing at that point in time. But that is that's a little different. Anyway, so now I think we've pretty much covered what we wanted to cover here. We're making some small advancements, and we see the spin network. This is what it looks like. It's pretty fascinating. This is in fact the Calabi-Yau manifold right here. Everything is trying to essentially form around this perfect spiraling shape. If you spiral this around time, you're going to get the Riemann zeta function. You're going to get the shells, the golden ratios, and some crazy stuff. Besides this, there is one sort of thing where this is heading me towards. As you can see, we have these imaginary zeros popping up at 1/2 plus IT. This happens if we sum up all the L's over here. But what if we were to sum up all the energies? I was going to do that over here. I believe we have this already completed though. This is sort of what we have to take. The next step is to sort of understand the quantum Hall effect and see how we can manage to derive a zeta function from the energy levels of the quantum Hall effect over here. And in order to do that, all we have to do is actually sum all the energy levels. I haven't done this here on this sheet, but I'll have to go and do that so that way we can discuss this in the next video, essentially. This is where we need to develop the zeta function for the energy levels here. As you can see, we have the setup, a half, there's an n. All we need to do is get the time involved and get this into a zeta form. But what's really interesting about these quantum resistance and Hall effect is that it actually is connected to the fine structure constant A. Because if we take the inverse of the R Hall, we have E squared over H, and then there's this integer here, which tells us the number of filled lambda levels. Anyway, the point is that if we have E squared over H, it's part of the fine structure constant. And then what is all this 2 pi over 4 pi epsilon c here? Well, the epsilon c is actually the impedance of free space. So this is just the electric magnitude divided by the magnetic magnitude. And what we're doing is we're actually taking 1/2, see 2 pi over 4 pi is a half. That gives us the half-filled lambda level. Yes, that's correct. V equals a half. And then what happens is that we actually divide the impedance of free space by the quantum Hall effect, or the quantum resistance here, and we get alpha. We get the impedance, we get the fine structure constant. Um, it's just an observation I've made, and it's quite. I'm sure this is common knowledge. I don't think that this is something new, but it's definitely here, and we clearly see that there's something happening at the 1/2 filled lambda level, and uh, and that gives us this 1/2 energy situation, I think. But we have to figure out what these halves are doing here, whether they have anything to do with spin of a half, or whether they have to do with that 1/2 point of the Riemann zeta function, or what these halves are doing. That's our assignment and what we need to do for next time. So hopefully this was interesting. You know, you'll have